the Richter scale.
Okay. So, a lot of times when you see earthquakes being reported, you will see something about this earthquake measured 7.2 on the Richter scale, or it measured 3.5 on the Richter scale. You always see these Richter scale measurements, okay? And most of you might know enough about Richter scale measurements. You know, anything, once you start getting above 6 to 7, earthquakes get pretty bad. I mean, there's only been a few over 8 ever. So those are the worst scores to get as far as the amount of damage that's going to be done, okay? But what does that really mean? What does it mean mathematically? What does it really mean when they say it was a Richter scale measurement of 5.5 or whatever, okay? Well, here's some math behind it, okay? The Richter scale values are equal to 0.67 times the logarithm of 0.37 where E is the amount of energy, okay? The amount of energy that is released in that earthquake, okay? Obviously, the more energy that's going to be released, the more damage it's going to be able to do, okay? Plus 1.46. So what we're going to do here if you see the map on page 521, we're going to compare a couple earthquakes. One of them that measured a 4.1 in California, and then we'll use the one that was in Athens, Greece. That was a 5.9. Okay, so we're going to use a 4.1 and a 5.9 and compare the two of them. Okay? So first of all, let's use the 4.1, the one that was in California. So what I'm going to do is, they told me the Richter scale measurement was 4.1, so I'm going to go ahead and plug 4.1 in for R, and then I'm going to solve that equation for E to see how much energy that 4.1 earthquake really emitted, okay? So I plugged in 4.1. I'm solving for E. What do you think I should do next? Subtract the 1.46, so I did that. Then what do you think I should do? Divide by 0.67, yep. So then, here's where we're sitting. We're sitting at this 3.9402, whatever, equals log of 0.37 I'll let you kind of get that far. So we're sitting here at this stage where we have something equals the log of our variable, right? Well, the only way to get that variable by itself, to solve for E, is again going to be to change forms. This equation right here at this level is in logarithmic form. Okay? This is in logarithmic form. So to get it out of logarithmic form and able to get our variable out from being logarithm so we could actually solve for that variable, you want to change to exponential form. Alright? So what you need to think is, okay, well, what's my base on my logarithm? You don't see one, so there's really a 10 there. And then you take that base 10 and raise it to the number on the other side of the equal sign, raise it to the exponent. So 10 raised to this power equals 0.37 So 10 raised to this power equals 0.37 Get that answer, divide by 0.37, and hopefully if you're working through it on your calculator, you would be able to get 23,555.74 kilowatt hours. So the amount of energy that this earthquake releases is over 23,000 kilowatt hours. Any questions on what we did there? Figure out the difference in energy released in that one in Greece then, the 5.9. So go ahead and solve for E when the Richter scale value is 5.9. Calculate what?
10 to the power equal 0.37.
Just 10 raised to the, and then just type 3.940298507. If you have a previous answer button on your calculator, that's a little faster than having to type it all back in, but you definitely don't want to round your answer.
I got it.
Have you divided by 0.37 yet?
No,
We need to divide both sides by 0.37 to get E by itself.
I got it.
Get it? Okay. Good. Alright, so this was the 4.1 earthquake in California. See if you can calculate the 5.9 earthquake in Greece. Once you think you have your answer, go ahead and compare it to a neighbor. If you're stuck, ask, or ask a neighbor. About one more minute here, guys. One more minute.
So we raise that and then divide by, we'd take like 10 raised to the 6.6 and then divide it.
So now you gotta change forms. What's your base? No, your base. No, the base. 10. Even though you don't see that there was really a 10 there. So then we gotta say 10. No, log 10. So you're basically right here at this step. Tough to solve for E when E is being logarithm. So what you need to do is you need to change forms. There's really a little 10 here on your logarithm. And to change forms, you take that base and you raise it to the number on the other side equals.
That's for the,
So that's 10 raised to this power equals
which one?
0.378. So I don't know what you have for here, but you're going to say 10 raised to whatever that number is equals
Yeah, I thought it was
0.378.
the basics.
Change forms.
Yeah, that's the one.
268.9. That's really good. 268.
Supposed to do 6.6 for that. The other one in Japan.
Pretty sure Japan's had more than
10 raised to this. No, around 10.
Yeah, California's had more than 4.1.
Yeah.
It's just
Japan didn't actually have one. Japan was the ocean.
So you couch it around for you. Mine.
I don't know.
But you would probably pull up something stupid. You know what?
what'd you get for your answer?
What's that? Oh, yeah.
Yeah, I got 0.9.
I got 0.89.
She's like, she's 0.01.
So I got 11,446,269. Okay? Now, okay? So all we did was change this number from a 4.1 to a 5.9.
And we're bigger than
And our 23,000 became over 11 million. How could changing this by just simply 1.8 change the power or the energy released by such a drastic amount? Mathematically, why is that happening?
Because you're raising it to a higher power.
You're working with exponents, right? You're working with logarithms, and therefore you're raising it to a much higher power, okay? In the one that you guys just did, you took...
What are you doing?
Install later, or remind
We
me.
can install it now.
In this one, you took 10 and raised it to 6.6 something, right?
Yeah.
In the previous problem, we took 10 and raised it to 3.9. That's going to be where your
It's double.
significant difference occurs. This is about 10 to the 4th power. 10 to the 4th power, 10 grand, right? 10 to the 4th power is 10,000. 10 to the 6, almost 7 power, that's between 1 million and 10 million. Okay? So just that small difference, a 3.9 to a 6.6, that's a huge difference when you're talking about an exponent on a 10. Okay? That's a huge difference. And that is why the two numbers are actually coming up so different from one another.
Yeah.
Okay? In fact, this right here is 500 times bigger than this. Which is exactly why this right here is 500 times bigger than the previous one. That 23,000 or whatever.
How'd you get 500,000?
Take this divided by this. To know how many times larger something is. If you take this, and I don't know what this decimal was all the way, but just roughly, and I'm using 500 as a rough estimate, but it's like 501 or something like that, okay? But if you take this divided by this, you get about 500, okay? Which is exactly how many times stronger this one is than the other one. It's all because that's the difference in the power that you put on the 10, okay? And I ask you a question like that on your test. I ask you to compare a couple Richter scale values, and then I ask you why is changing the Richter scale value by 1 or 2 such a significant difference. And it has to deal with the fact that you're actually taking 10 and raising it to a different numbered power. Okay? So that is why there's such a huge, huge difference. So just by changing it that 1.8, all right, you actually had an earthquake that was 500 times stronger than the other one. That's all because you're working with logarithms, and logarithms are really exponents. In this case, exponents on tens. So every time you raise it by 1, you're potentially getting 10 times stronger. Okay, or more than that actually. All right? Any questions on that type of problem?